Good morning, students. Uh, Today we are discussing in this class about the closed packed structures. We know that solids in which the constituent particles are held together by a strong intermolecular force. Now, we study about the closed packed arrangement of these constituent particles in solids in three different ways. Okay. So first, let me study the closed packed structures in one-dimensional, two-dimensional, and in three-dimensional. How the particles are arranged in one-dimensional, two-dimensional, and three-dimensional. Okay. So first is the one-dimensional. One-dimensional arrangement of the constituent particles. And students, here the constituent particles I am considering as in a hard sphere. Okay. Let me show you. In one-dimensional, the arrangement of these particles is in this way. That is, the one particle is placed in touch with the other, either it is along x-axis, y-axis, or z-axis. Only one type of the arrangement is seen in one-dimensional. This is the arrangement of the particles. Okay. So here, each particle is in touch with other two particles. For example, this is the particle, it is in touch with the two particles. If I consider this one, this is in touch with the two particles. Therefore, we got the coordination number of one-dimensional arrangement is 2. And since here, the coordination number is defined as the number of nearest neighboring atoms to that particular atom. So neighboring atoms, they are called as a coordination number. So here the neighboring atoms for any particular atom is 2. So therefore the coordination number is 2. This is the one-dimensional arrangement of the constituent particles. Now let me go with the two-dimensional arrangement of the constituent particles. So here take the two-dimensional, second one is a two-dimensional arrangement. See, in two-dimensional arrangement, first I will arrange the particles in along x-axis, and then I place the second row exactly same as the first one. Like that, the second ball is placed exactly below the first one, like this. So this is the type of arrangement. Okay, so here the first row, this is the first row, and the next the particles are arranged in x-axis, then the particles are arranged in y-axis. So first row is exactly same as the second one. If I call the first row as an A type of arrangement, okay. So second row is also exactly same as the first one. So second row is also an A type, third row is also an A type of arrangement. So here in two-dimensional, this type of arrangement is called is an AA type of arrangements. This is the first point that we have to write. Okay, so in two-dimensional arrangement, the type of the arrangement is AA type. Next is, let me find the coordination number. So the coordination number in this two-dimensional arrangement is find the nearest neighboring atom. So coordination just now I have defined, it is the nearest neighboring atom to that particular atom. Find the nearest neighboring atoms to any atom. So for example, the neighbors of these atoms are the atoms which are in touch with that. Those are called the neighbors. Okay, so here this is the one atom which is in touch with that, and this is the second one is also in touch with that atom, and this is the third. Okay, and this one is the fourth. So there are 4 atoms which are in touch with that particular one. So therefore the coordination number in this type of arrangement is 4. And since this type of arrangement is named as square close packing. This is named as square closed packing. Okay. It's called square close packing only because when we join the centers of the neighboring atoms, okay, when I join the centers of all these neighboring atoms, it forms a square-like structure. Okay, so it uses a square-like structure. So therefore, it is called a square close packing arrangement. Okay. And another one point I am adding here, that is, there is some empty space present between these arrangements of the atoms. See, these are the atoms are closely packed, but there is some empty space. Let me highlight that empty space here. This is the empty space where no atoms are present. Okay, so those empty space we call it as voids. Okay, so these are the voids. The empty space present between the row, these are called as voids. And since here the shape of this void is just observe the shape of this void is just like in a square. So therefore it contains a square type of voids. Square voids are present. Okay. That's another one point we make for this two-dimensional arrangement. And next one is the fifth point. I'm here defining the relationship between the number of particles and the voids. Okay. See, how many particles will create how many voids? For example, if I provide 100 balls, so if I arrange that 100 balls in this type, AA type of an arrangement in a two-dimensional manner, then how many square voids are formed by that 100 particles? Okay. So to find out that, let me consider this square. This is the square. See, in this square, let me count the total number of particles present in this square. See, there is a one complete particle. This is the one. Okay, and 1/4 of this particle is present in this square. And similarly, 1/4 of this particle, and 1/4 of this, and 1/4 of the fourth particle. Okay, so only 1/4 of the particle is present in this square. So therefore, the total number of particles present in this square is 1. Let me write the particles is equals to 1 complete sphere and 1/4 of the 4 spheres. Okay, so 4 into 1 by 4. So that is equals to 2. The total number of particles in this square is 2. Now count the voids. Voids is empty space. Okay, so how many square voids are present in this square? Sorry, in this square. So here, this is the one square void. Okay, so half of the square void is present in this square, and here half of this square void, here half of this square void, and here half of this square void, and here half of this square void. That means, so there are 4 half square voids are present in that square. So therefore, let me write the total number of square voids are 4, and each square void is only half is present in that square. So therefore, it is equals to 2. Okay. So here the 4 particles will form 2 voids. Therefore, the particle void ratio is particle void ratio. You can write it is 2:2 or it is 1:1. Okay, so that indicates that shows the particle void ratio is 1:1. That means if 100 particles are arranged in AA type in two-dimensional, so then 100 particles will create 100 square voids. So this is about the two-dimensional arrangement. This is the first arrangement. There is another one type of arrangement. Let me show you that.
Next is in two-dimensional. There is another one type of void. There is the second one is
hexagonal closed. Closed packing. So just now we observed the square closed packing. There is another one type of arrangement in two-dimensional manner, that is the hexagonal closed packing. So let me take the first. We arrange the particles in one-dimensional. Next, so the next sphere is placed in the depression of this first one. So here, Okay. See, this is the first layer. If I call that as an A type. So here the second row is placed in the depression of the first one. So here in between these two balls, so the next ball is placed in between these two balls. So this arrangement is completely different from the first one. So let me define this as a P type of arrangement. Okay. And the third one is exactly the same as the first one. So third row again it is an A type of arrangement. Okay. So third row is exactly same as the first one. So third is an A type of arrangement. Then the fourth one is exactly same as the second one. So then fourth row is called as a B type. So this type of arrangement we call it as an AB type of arrangement. Okay, first let me write the type of arrangement is AB type. And second point is about the coordination number. And so for coordination number, find the nearest neighboring atoms to any atom. Find the neighbors of any particular atoms. For example, this is let me consider this is an atom. So neighbors of these atoms are 1. So here this is also in touch with that 2. This is also in touch with that 3. This is 4 and 5 and 6. Right? So all these are in touch with that. So the neighboring atoms to that particular atom is 6. So therefore the coordination number here is 6. Right? And since this type of arrangement is called hexagonal close packing, it is because when we join the centers of all the neighboring atoms, it forms like a hexagon. See. It forms like a hexagon. So therefore it is called as a hexagonal close packing. Closed packing arrangements, like closed bracket structures. And since the fourth one, the type of the wires form. Okay. So here in last square closed packing system, we observed we observed the square wires, and here the wires are of the shape triangle. Okay. So this is the triangle wire, and this is also a triangular wire. See, these all are the triangular wires. So here we call the wires, they are triangle like shape, so the wires are called triangular wires. Triangular wires. Now the relationship between the particles and wires. Okay. So how they are located, so how many particles will create how many wires. Okay. So to find that, let me consider this hexagon. Okay. So in this hexagon, the total number of particles present. Okay. So it means the particle wire ratio. In short, I am writing the P and V ratio is. So the total number of particles present in this hexagon is the one complete particle, and see this sphere. So here 1/3 of this sphere is present in this hexagon. Similarly, 1/3 of this, 1/3 of this, 1/3 of this, 1/3 of this, 1/3 of this. Okay. So there are 6 neighboring atoms which are present in this hexagon. So all are contributing their 1/3. So therefore the total number of particles are 1 plus 1/3 into 6. Okay. So this equals to 1 plus 2, that is 3. The total number of particles are 3. Now the total number of wires are. Okay. So let's check how many triangular wires are present in this hexagon. Okay. See, this is a complete triangular wire is present in this hexagon. Similarly, this is a complete triangular wire. This is also complete triangular wire. Okay, so there are totally 6 triangular voids are present in that hexagon. 1, 2, 3, 4, 5, 6. Okay, so therefore the voids here, the voids are 6. Okay, therefore the particle void ratio is 3 is to 6 or it is 1 is to 2. Okay, this is the particle void ratio. Okay, that means if this type of the arrangement is done by using 100 particles or 100 spheres, that will create a 200 of triangular voids. Yes. Next one is, let me go with a 3-dimensional arrangement of the constituent particles. Okay, in 1-dimensional, we have arranged the particles along x-axis. Okay. And in 2-dimensional, we arrange the particles in x-axis as well as y-axis. So now, I am using, in 3-dimensional, I am using the 2-dimensional arrangements. Okay. So in 2-dimensional arrangements, we have stated about the 2 types. One is the square close packing, another one is the hexagonal close packing. Okay. Now, let me consider the square close packing arrangement in 2-dimensional as a 1 layer. Okay, so in 3-dimensional, so this is the 1 layer of close packed structures in 2-dimensional. That is, we already studied, there is a square close packing structure. In square close packing structure, this is the first layer, and this is the second layer, and this one is the third layer. So like that, these are of AA type of arrangements. Okay. And next, there is another 1 layer. The same layer is placed exactly above of this first layer. This is the first layer. Okay, so I call this as A type of layer. Okay, and the same layer is placed exactly above this. Okay, so the same type of arrangement is placed exactly above this. So first ball, so on this another one first ball is placed. So that may looks like this. So it's in a 3-dimensional structure. Just imagine. So there is a 1 square close packing structure on which there is another 1 layer is placed, on which there is another 1 layer is placed. So and next third layer, like that. Is in a 3-dimensional arrangement in a square close packing structures. Now, since the important is in this arrangement is also what this type of arrangement is of AA type of arrangement. Because so first layer, if I define that as an A, and second layer is also exactly same as the first one, and third layer is also exactly same as the first one. So therefore, this type of arrangement we call it as an AA type of arrangement. And since here, the next point is about the coordination number, and this arrangement is also called. So this arrangement we call it as a simple cubic close packing arrangement. Okay, I will come with that. It is also called simple cubic closed packing. Okay. It's called simple cubic closed packing because when I join the centers of neighboring atoms, for example, when I join the centers of these spheres, okay, see, these are in touch with each other, these two, and this also sphere is in touch with each other. So next, this is the behind, this is also in touch with that sphere. So this sphere is in touch with here. Okay. See, what we observe is just looks like a cube which contains total 8 spheres at their corners. Okay. So if there are 8 spheres are present at the corners of that cube, so that arrangement we already defined as a simple cubic. Okay. So or that in itself is defined as a simple cubic in itself. Okay. So here is also the atoms are present at the corners of the cube. So therefore this arrangement is called simple cubic close packing arrangement. And so the coordination number. Okay. Since here the coordination number, let me show you the neighboring atoms to that particular atom. Say in simple cubic there are totally 8 particles. Let me take the 8 corner particles. These all are the corner particles. And these corner particles are in touch with each other. For example, if I consider this sphere, so this sphere is in touch with here 1, and this sphere is also in touch with the second corner particles, and also this sphere is in touch with here. There is the third one. Okay, so there are 3 particles are in touch with that. Okay. Yeah, the third one. Okay. Now, this is in a single layer. Okay. If I place another one, so this particle is also in touch with just above, and also in front, touch with another one particles, and also here along y-axis, along z-axis, and also along x-axis. Okay. So there is another one unit cell. It is also in touch with that. There is another one unit cell above this cube, where another particle is also in touch with that. Okay, because this is the corner for these 2 unit cells. Okay, so there is another one cube above this. There is another one corner particle also in touch with that. That means there are totally 6 corner particles. They are in touch with that particular one. Therefore, the coordination number is 6. Okay. So this is the one type of square close packing arrangements in 2-dimensional. Next is another one type of arrangement in 3-dimensional, that is hexagonal close packed structures or hexagonal close packing arrangement in 3-dimensional. In 2-dimensional also, we studied about the hexagonal close packing structures, where we calculated the coordination number. Coordination number is 6 in 2-dimensional, and the arrangement is of AB type. Now, let me take the hexagonal close packing arrangement in 2-dimensional as one single layer. This complete as one layer. Let me define that layer as an A type of layer. Now, to make a 3-dimensional structures, let me arrange another one type of hexagonal close packing structure above this layer. Right? And next, another one layer below this layer, or above that second layer, and next layer is above that third layer. So it will give me the complete 3-dimensional arrangement in hexagonal close packing structure. See, the arrangement is of 2 types. One is hexagonal close packing, so it is also called HCP, hexagonal close packing, HCP structure. And another one is the cubic close packing. Let me discuss first HCP. Okay. As students, here this is hexagonal close packing. We know the hexagonal close packing structures have the triangular wires. These are the triangular wires. Students, here there are 2 types of triangular wires are seen. Let me define, if the triangle is of this type, let me define that as an A type, small a. If the triangle is of this type, okay, so this type of a triangular wire, that is called as a B type. So there are 2 types of triangular wires. So this is A type and this one is a B type. Right? Either this is the B, and this one is the A, this is A, and here is an B. This is the B. Okay. So each sphere, it is surrounded by 3 A type of triangular wires and 3 B type of triangular wires. Okay. Now, if I place the next layer exactly, so the next layer is in such a way that which covers only the A type of wires, that is, this is the sphere which covers completely the A type of wires. the next ball, and third one. Okay. See students, this is the second hexagonal close packing arrangement. Okay. So and it covers only A type of words. Okay. Therefore, this is the second layer. Okay, is in a different layer. So this layer, let me call this layer as in a B type. Okay. And the next third layer is exactly same as the first one. Okay. So then that layer once again is called as an A type. And the fourth layer is exactly same as the second one, that is the B type. Therefore, this type of arrangement is called AB type of arrangement. Let me write the first point. What this is an AB type of arrangements. Now, second point is about the coordination number. Okay. See, for coordination number, let me consider one small. I am taking 6 neighboring atoms in a plane in a first layer. For this particular atom, I am calculating the coordination number. For that particular atom, there are 6 neighbors. Okay. And the second layer is of this type. Okay, so which covers only the A type of wires. Okay, this is the second layer. It covers only A type of the wires. That means it has in touch with 3 spheres in the second layer. Okay. That particular atom is in touch with the 3 spheres above that layer, and similarly the same type of arrangement is below that layer. So where another 3 particles are in touch with that particular one. Okay. Therefore, the coordination number here is 12. Okay. Since here this is a particular one particle. Okay. Let me highlight that particle for which I am calculating the coordination number. This is the particle. Okay. So for this particle, the neighboring atoms in a plane is 1, 2, 3, 4, 5, 6 in a plane. And there are another 3 particles are in touch with that. Those are above the plane. Above the plane, there are 3 particles. This is the 1, 2, and 3. Okay. And same type of the arrangement is below that plane. That means another 3 particles are also in touch with that. That means 3 particles below the plane, 3 particles above the plane, and in a plane 6 particles. Therefore, the coordination number in hexagonal close packing system is 12. And next students, the type of the wires present. So the type of wires, for that let me consider only these 3 spheres, 1, 2, and 3. Okay. So let me draw this. Let me take only one triangular wire. So here I am taking this triangular wire here. This is the one triangular wire. Okay. So there are 2 types of the wires are present. One is of A type of wires, another one is of B type of wires. So A type of wires. So here I am taking A type of wires. See on this, above this A type of wires, there is another one sphere. Okay, this is the one sphere or one ball which covers the A type of wires. Okay. So there is some empty space is present between these 2 layers, between the first layer and the second layer. So first layer, there are 3 balls which constructs a void. There is another one ball is placed on that layer. So that means there is some empty space present here. Okay. So that void is called a tetrahedral void. Okay. That void is called a tetrahedral void. So here the third one, there are tetrahedral voids. So tetrahedral void It is because when I join the centers of all these spheres, it forms like a tetragon. Okay, so let me show you. When I join the centers of all these spheres, it forms like in a tetrahedral, tetragon. So this is the structure is like this. When I join the centers, it forms the structure like. Okay, so that is called a tetragon. Therefore, that type of the empty space is called a tetrahedral void. Okay, and there is another one type of void is present. So there is B type of voids. A type of voids are the tetrahedral voids, and B type of voids. Okay. Let's look at here in this diagram. So B type of voids are surrounded by 6 spheres. In a plane, there are 3 spheres. Okay, so this is a white chalk. So this is 1, 2, and 3. Okay, which construct a B type of voids, and that B type of voids is covered by the another 3 particles above the plane. So these are the 3 spheres, 1, 2, and 3. Okay, let me write it. So here, this is the B type of void. Okay. So in the first layer, they have a B type of void, and in second layer, this is the second layer. Okay. So which have covered by another 3 spheres. Okay. So this empty space is of the shape of octagon. So therefore, it is called an octahedral void. Okay, that B type of void forms octahedral void. Okay. So it is called octahedral because when we join the centers of all these spheres, it forms like an octagon. Let me show you. When I join the centers, these are the centers of first 3 spheres. Let me join this. Okay. And next, another 3 spheres. These are the 3 spheres of second layer. And also let me join these 2 also, first and second layer spheres. Or it forms like an octagon. So the octagon structure, you know. Like this. If you got as an octagon, so the shape of that empty space is like an octagon. So therefore, it is called an octahedral voids. So this is the arrangement seen in HCB. Instance, the particle void ratio. The 5th point is about the particle void ratio. Particle void ratio. If I consider there are n type of the spheres are arranged in a hexagonal closed packing structure in a 3-dimensional manner, that forms n type of n number of the particles will form the 2n number of tetrahedral voids and n number of octahedral voids. This is the particle void ratio. Okay. So if I use n number of particles, okay, and arrange those in a hexagonal closed packed manner, okay, in a 3-dimensional, that forms 2 2n number of the tetrahedral wires and n number of the octahedral wires. Okay. Say for example, there are 1000 particles are used, okay, and 1000 particles are arranged in a hexagonal close packed manner. Okay. So in a three-dimensional, so 1000 particles will create 2000 of tetrahedral wires and 1000 of octahedral wires. This is about the hexagonal close packing structures. Yes, you have to remember these 5 points about this hexagonal close packing structures. Similarly, there is another one type of close packing structures. There is a second one called as a cubic close packed structures. In short time, we write that as a CCP. Cubic close packed structures. In cubic close packed structure is also same. The arrangement is only the changes. So in cubic close packed structures, the arrangement is a ABC type. Right here. In second one, there is a right here. The hexagonal, and next one is the cubic close packed structures. In short, we call it as a CCP. Okay, so cubic close packed. In cubic close packed, the first layer, we define the first layer as an A type of hexagonal close packing, and the second one is exactly same as in HCP, that is in a B type, and since the third one is, okay, so in third layer, where the spheres are placed, the next layer is placed which covers the B type of wires formed in the first layer. Okay. That means the third layer is placed on the wires, so on the B type of wires formed. Okay. So that arrangement is different. That is because in a C type of arrangements. Okay, just imagine that arrangement. The first layer which covers the A type of wires. First layer which forms the A type of wires, and second layer which is placed on the wires, A type of wires formed in first layer, and the third layer is placed on the B type of the wires formed. So that arrangement is of an A C type. Is an exactly different from that AB. Okay, therefore it is called ABC type of arrangements. As the next, the coordination number is also same. In CCP, coordination number is 12, and the wires present here is, there are two types, tetrahedral and octahedral wires, the same type of wires, and the particle ratio is also same in CCP arrangement. There n number of particles will create 2n number of tetrahedral wires and n number of the octahedral wires. So everything is same, but only the difference here is the arrangement. The arrangement in cubic close packing, it is ABC type, and in hexagonal close packing, it is an AB type of arrangements.